invariants. Universal can mean many things, but we are in Waseda University, so it should be Jun Murakami style universal invariants coming from UQSL2, such things. I actually learned this from Otsuki's book. He has a very nice account of this. You start with a ribbon hop algebra and then you can make universal invariant. I realize this is not as universal as you get. You can do much more universal by forgetting about the Lie algebra or the ribbon hop algebra and just work with diagrams. But here I want to do concrete computations, and algebras are useful for doing concrete computations. So this is only half universal. And so what does it do? It will produce a computable generalization of the Alexander polynomial. And so in some sense, for not theory, the Alexander polynomial is a foundation of many things. I think Hitoshi Murakami once told me it's the seed from which many quantum invariants grow. Do you remember? Quote from 2007. But anyway, I want to grow this seed and show you how you get something slightly more interesting that's towards the Jones polynomial, but definitely not the whole Jones polynomial. And this is joint work with Dror Barnatan. But I must say most of the ideas are his. He was already studying this kind of quotients before I was born, I think. But so the mistakes are mine, ideas are his.
Roland.
Yes.
When you born?
1982. So there was pre-Jones, but this is on camera, so I'd rather not go into it. I was born before the Jones polynomial, but not very much so. Anyway, so what is the plan? So I want to make a little outline, plan of my talk. Well, first part of the plan is to make a handout. So I want to ask, does everybody have a handout? Otherwise there should be, there are more on both sides of the, and there are also more here. I'll make something. But so the point of the handout is that it's hard to read, but maybe if I got you interested during the talk, then you can look at some details that I will fail to write or will just not write correctly. Hopefully the handout is correct. But the handout also contains a reference at the very end to another handout by Dror that is, I think, twice as big and twice as colorful, because he gave a 4-hour talk and I'm only giving a 1-hour talk if I do well. So if you feel anything is unclear, then this is also definitely a place to look. But so what is my plan? I want to first consider an algebra or algebras really, Dn related to UQ. This is maybe for the purpose of this talk, this is the foundation. This is where things start. But of course you could dig deeper and ask where does this algebra come from. But for the interest of time, I'm just writing down the commutation relations here. But it is essential for building up this universal invariant. So after that I will build up. Don, I think you're missing a handout. Is this correct?
No, it's good.
You're just waiting for me to say something interesting. Okay. Anybody else need a handout? There are still many left. So I will talk about this universal invariant, and then I will focus on the simplest case, on using these normally ordered exponentials. So that's a very simple thing, right? Computing so the goal of this talk in some sense is to compute the Alexander polynomial of the trefoil. Well, everybody can do that. But the point is to do it in an interesting way that generalizes and also illustrates what you would do in general. Any questions so far? Okay, so I'm going to pass to the first line of the handout, which reads the algebra. And this is important enough that I want to, even though everybody has it on the handout, I want to write it down because I'm excited about this algebra. So it's a sequence of algebras, Dn. So for n in n, the natural numbers start with 1, I suppose, here. Dn is an algebra over Q, and now comes the interesting part, Q epsilon. This is Q polynomials in epsilon that's squared to, not square, sorry, nth power is 0. So this thing, maybe I can abbreviate to Q epsilon. Qn. There should be an n in there, yes.
It doesn't depend on epsilon, it depends on n.
That's absolutely right. I may still write it epsilon because I did in my handout, but it was late last night. So I completely agree with you.
Just trying to show that I got one. Okay.
Thank you. Okay, but at least, well, this is the ring we're working over, and so in some sense the only novelty is here that we have some nilpotency, and we introduce some nilpotency in the computations we do with UQSL2, or really UQGL2. So let me write down the generators. So this is algebra over this ring, generated by. So I'm not using the standard letters, but maybe this should be E, F, K, H or so. But well, I'm sort of used to these letters now. So these are 4 generators, and satisfying commutation relations that you should recognize. Maybe the first one is not so easy to recognize. This is the most interesting one. That's why it comes first. And notice the epsilon, but for now maybe set epsilon to 1, so then you would get the usual.
It's not defined, it's 0. What's B?
B. Ah.
In the handout there is also B. A capital B.
Capital B. My apologies. I keep switching between capital B. So in the handout, the small b is a capital B. Thank you very much. And later I will switch back to my lowercase b, but I did this too many times. So please tell me if there are more glitches. But I hope the next one at least is clear. For many people prefer 2 here, and this is the relation for the Borel, the upper Borel in SL2. It's 2-dimensional Lie algebra, it's non-commutative. So this is maybe the most important relation here, and all the rest comes from making a quantum double construction. So we have WC, we have WB, this is capital B, and it does exactly the same thing but with an epsilon, so that's mildly interesting. And UC is the same thing, this is the other Borel, so it is minus U and U capital B equals epsilon. So in some sense the capital letters here are for the dual or for the lower Borel, and the lowercase letters are for the upper. And so this is really doubling this little algebra here with respect to this extra nilpotent element epsilon.
So you need some completion to exponentiate.
I agree. I need some and you can see in the handout there's some little hack here and there. I will ignore it for the sake of argument, but indeed we need some completion. So H adding completion just as in UQSL2. So I would introduce a parameter H in equating. Yeah, no, but this is a good point. I'm glossing over this. So I'm going to write down many infinite sums that are.
use the algebraic nature of your theory.
I would like to, but really I think right here I'm just being sloppy and I'm hiding the grading and the age at completion. But I agree, it would be nice to take the dual and work algebraically. This is definitely worth doing. But here I just want to make the point that this looks like UQSL2, except here usually you have another denominator, something like Q minus Q inverse, and then this is and B equals C. And you see there is a central element. And this is small b. B equals capital B minus epsilon C, if I don't get it wrong. Yes, so this is a central element. That's easy to see because you see the C and B do exactly the same thing except for an epsilon. So if I put the epsilon here, then this will make all the computation relations vanish. So this is a central element right here. And in the construction of UQSL2, as usual, you would this represents the double Cartan, and so this gets quotiented out.
I think you need a minus epsilon u in the last line if you want that to be central.
Thank you. Yeah, because I did say that they should act the same, except did the handout get it right?
Yeah.
Yes. Thank you very much. Maybe I shouldn't have written anything. I just told you about the handout, but in some sense, it's nice to see them appear here. So it's a relatively simple algebra, and I want to pay a special attention to, we focus on, this is n equals 0, sorry, not n equals 0, n equals 1. N equals 1, which means epsilon is equal to 0, so we get some particularly simple algebra. And n equals 1, sorry, n equals 2. This is epsilon squared equals 0. So these are the two cases I want to focus on. And so this one will produce Alexander. And this one will produce something new. But it's hard to say the word new in mathematics. Nothing is new in mathematics.
But what is the whole algebra structure here?
That's a good point. I did write one thing in the handout. So this is a quantum double construction, right? So dn, d stands for double. So dn is the quantum double of this WC. So the universal enveloping algebra. This is not U. This is universal enveloping algebra. WC. So of the Roland, but now with.
Sorry, U is the universal?
Yes, so this is an algebra, this is a Lie algebra.
It's written that it's the universal algebra. Using algebra of U is a little confusing.
It is very confusing. It's a calligraphic U. And in a moment,
But do you use the standard Hopf algebra structure here?
not quite. So what I wrote in the handout was that I took the bi-algebra structure, which is sending W to epsilon. So it's epsilon times the standard bi-algebra structure.
And which coproduct corresponds to?
And I think the rest is fixed. If I have this and that, then I think the rest is fixed by asking for duality. So I want them to be dual.
But what is the
dually.
coproduct finally?
Okay, yes. I did not write that down. So the coproduct for W is interesting, for C is not so interesting. And so for W it is, so the trivial one would be this. But instead I put e to the epsilon b, I think. Well, it should be related to this, so I think epsilon c. Yes, epsilon c should be it. And so again, this is the pretty much the standard quantization of the if you remove the epsilon. Sorry, in your paper with Rashitikin from 2004, you write down a quantization for making UQ GL2, and so this is very similar. It's just I made it slightly asymmetric, but this is not a big deal. So I'm not trying to do something radical. I'm just introducing this epsilon. That's all. And this epsilon is going to cut the quantum invariance down to size, so we can do some more computations for more knots. Maybe not just 17 knots.
It looks like Jordanian deformation of.
Maybe we should talk about it. I don't know. I don't know all the deformations. There seem to be so many. So, yeah. So in this sense, it may not be new at all, but it's new to me, and I would like to tell you about it.
By new you mean the two loop.
Well, I don't know yet. There is a little footnote saying there's a footnote that there are expectations and that nothing new is under the sun.
Little C. And C is group-like.
Yes, C is group-like. I did not write it. Yes, so we start with the standard quantization of the universal enveloping algebra of the two-dimensional piece, and then we make this quantum double, keeping track of epsilon and forgetting about the H-adic topology. I apologize.
Sorry, which was the Roland? So which is the diagonal touch?
C.
C is the.
So this must be this is maybe E H. That's maybe better terminology. So E is W.
So delta C is C delta C.
Yes. Oh no. It's not. It's Lie algebra like. It's not group like. Right. So yeah. It's primitive. More questions? This is an important point, and so I would be very happy if somebody could tell me more about this algebra and maybe its representation theory. I was not so lucky with the representation theory so far, but maybe I wasn't looking for it either. I was focusing on this universal invariance, and that's what I want to talk about next.
Then what is B? The U is F. U corresponds to F.
Yeah, so B is the doubled cartan. So we have two. We have H and A, maybe H prime. And then quotienting out the central element would be setting them equal to each other. So we get too much and we quotient out. And so I said I would like to focus on the cases n equals 1 and 2, but maybe 0 is also interesting, right? Or infinity, I don't know how to say it, but I mean the case where you have where epsilon equals 0. Sorry, epsilon equals 1, and so we're doing the standard, pretty much the standard thing. Just rescale a bit. And so what was mentioned by Stavros about this 2 loop, and maybe the Melvin-Morton-Rosansky that is in my little footnote. These are expectations that could be motivated from saying, well, we're doing some UQSL2 invariance. So it definitely, in that sense, it's a sequence of approximations to Color-Jones polynomials. And in that sense also to the Fourier conjecture, maybe, but maybe not. Because roots of unity are not so clear from this point of view. Okay, so I want to briefly introduce these universal invariants, but before I do that, I should write down the R matrix.
Can you compute this invariant for any node?
I wrote a program, so if you go to the very last part of the handout, the program has a Greek name, it's NIOB, and it computes from a braid presentation, and so I computed for 20 crossing braids. And so it seems interesting, but it's maybe too early to say much, but I can say that it definitely sees mirror images, so it's definitely stronger than Alexander is. It can, so the left-hand trefoil and the right-hand trefoil get distinguished.
Sorry, is it exactly the verified double of Borel?
Yes, with the epsilon. It's just over a different algebra of a different ring. But I'm doing something very standard here. My letters are a bit off, and I apologize for that. These are Dora's letters, so it's his fault. But yeah, I'm trying to do something very standard here. There are also other ways of getting to the same algebra, but I was trying to connect it to the world of Drinfeld. And so in the world of Drinfeld, if you have a quantum double, then you get an R matrix for free. So it looks very nice as far as R matrices go. This is also on the handout. So, and again, this is a divergent sum, maybe, if you're not careful about the completion of the tensor product. But in the interest of time and letters, chalk, I'm not going to write many H's that don't belong anywhere. So, and the way this is made is just from taking the co-pairing or the canonical element in the tensor product. So, C, W, J. So this is the R matrix. There is also the inverse of the R matrix, but I don't want to focus on it right now. It looks very simple. And this brackets are, my brackets are asymmetric. I suppose because my co-product I started with is asymmetric. So these are Gaussian Q numbers, not the symmetric ones. And so if I tell you this, then so it's just a geometric series. Then I picked a factorial.
So it's infinite dimension.
Yes, and so the invariant will be polynomials in B in this central element. That's how finite things are. And finite things are coming out of infinite dimensional objects because of these ordered exponentials. So I'm going to rewrite all these infinite sums as exponentials, and I'm just going to look at the exponents and the constant terms. And these are nice algebraic objects. So that's how, because this doesn't look very promising if you start calculating how this is. I mean, it looks okay, but now you have 10 R matrices, you get a big mess. So let's make a big mess, and let's do the trefoil from this point of view. And so there's a caveat here in this is unfinished work. So far. Universal invariant Zn. So this does depend on n. So it comes from Dn. Defined below. Only works for tangles. No. So there is an issue that's why I make the trefoil as a 1-1 tangle. So I'm not supposed to make closures, because closures will, at least in this way of looking at things, they will cause some trouble, and I haven't thought about it yet. There's probably some way of resolving this, but so far. If you want to talk about knots, you can always present them as a 1-1 tangle or a long knot. And so then no closed components are okay, but of course if we want to talk about links, maybe skein relations, then it would be nice to have closed components. Okay, so I wrote down in words what we should do to make this universal invariant. So what you do is you write down Cn defined by R matrix.
So can I ask?
Yes. One R matrix for each crossing. Yes.
So when did you modify it? So did you modify Borel with E and take quantum double, or
So
quantum double and modify?
So Borel is the same. but it starts happening at the if we make the Borel into a Lie bi-algebra. So it's the Lie bracket, it's the bracket on the dual, and then also the co-product. If we quantize that, that's where epsilon comes in. So it breaks the symmetry in. Good question. So I suppose this is a bit standard, but I find it hard to express it well. So if somebody knows how to explain it better, I would be very interested. But so my way of explaining is we take an R matrix for each crossing, and I'm just going to do it right here. So we have 3 crossings. They're all positive, so that's nice. So I don't have to worry about the R inverse here. But of course, if you have a net.
The existence of R matrix is non-trivial, then so you need to prove this is R matrix.
Can you repeat your question?
So if you take Dirichlet double with something, then you can have R matrix. But is this trick? So you broke the symmetry, right? In the definition of the n. So is it that? So the fact this is R matrix is follow, or it's non-trivial fact?
I think it follows over any ring. So the exact same proof still works. And in some sense, it's by definition, right? The quantum double is the algebra such that this thing, the canonical element, is solving Yang-Baxter.
So this is Dirichlet double also.
Yes. Yes. It's really the Dirichlet double. It's no more. It's just that there is something hiding in Q. Maybe I should say what is Q. I did not say that. So Q is my shorthand for e to the epsilon. This is. Sorry for forgetting about that. That's kind of important. Excuse me.
You did say it.
Well, I want to say it again because it's very nice. Because then all these silly Q factorials and Q things they get cut down to very simple objects. So for example, when n equals 1, then Q is just 1, and when n equals 2, then Q is just 1 plus epsilon. Right, so powers of 1 plus epsilon is very simple. So then you can still do Q calculus, but it will sort of be a mix of hypergeometric Q and Q hypergeometric functions. Then it's a nice mix, but it's much simpler than the full Q. And well, I don't know of a general theory of such hypergeometric functions, but I would be interested to hear if somebody knows. Okay, so I want to just give an example. I think this universal invariant is best explained by an example. And so remember no closed components. And the universal invariant from D is called Zn. Okay. So how do we make Zn here? Well, I take 3 R matrices, and we need to keep track of because I'm going to make many summations. It will be a 6-fold sum, so it's good to have some labeling of the knot. So let me label it 1. I don't know, 1, 2, 3. So I'm doing the lower part, 4, 5, 6. So what's really happening here maybe is that I'm cutting it into pieces, right? And now I'm just going to write down this sum 3 times. And I'm not sure that was a good idea. So maybe I can say something before I do that. So it's defined by taking an R matrix for each crossing, and then multiply along components.
You don't have to add some extra element for maximal or minimal.
I do, and I wrote it down, but I didn't. I wrote it down it's the very last part of the. So cap and cap get this e to the b plus epsilon c of 2. Yeah, so coming from the Drinfeld element, you're absolutely right. I'm just trying to hide. So maybe I can just do it, and you can try to follow if I get it right. So I multiply along the components, But the important thing is taking first tensor factor at overcrossing. Should I push it up? Okay, so I'll just do it briefly. So we start at 1. At 1, and this is the overcrossing, so I'm going to write down the first tensor factor. So the first tensor factor is u, j, and maybe I should put j1, so it's clear that I'm doing j1, b, phi1. So now I'm here, and then I'm at 4, and this is the undercrossing, so I'm taking the second tensor factor, but this is b4. So I take C, I, 4, J, 4. This is going to be a summation over J1, I1, and here I made the choice I4. Would have been nicer to do I3, I think. So we label by the overs, and there will also be I5. J5, and this doesn't look very promising, and maybe I should not continue this whole discussion, but let me do one more term. Here we get 5, and it's the overcrossing, so here I get UJ5 B I5. Oh, it's kind of fun. As June remarked, I should consider cups and caps, but in the interest of time, I'm going to ignore them. And here I get 2, which is the undercrossing, so I get C, I1, WJ1. We're almost there. 2, 3, 3 is the overcrossing, so I get U, J3, BJ, I3. Am I still okay? 3 and 6 is the last one, so why not do it? 6, and I label by 5, which is the overcrossing, J5. Great, so we have a 6-fold infinite sum, and this is computable.
Divided by all these factorials.
Thank you. Yes, and some of them quantum, and some of the i's are usual, and the j's are quantum. Okay, so this I think is well known, that you can always write such universal invariants, and this is where often the discussion stops, at least where I usually get discouraged.
Why don't you need tensor product in this formula?
Because it's a long knot, so everything gets connected.
Ah,
So I'm contracting every time.
I see.
Yeah, and this is maybe the cups and caps I was hiding. These are all contractions, but also connecting this piece of the R matrix to this piece of the R matrix contracts. But so in general, if I would have a time rule, then I would get as many tensor factors as the number of components. So usual Zn of t, where t is not a trefoil but some time rule.
I'm lost. This is the value here in this example. This sum.
Well, yes, in some sense, yeah. Thank you.
Right. So this is here.
This is
Then actually,
N of the trefoil, right?
so
Of the
now,
three.
to get an actual physical invariant, you have to use the relations in the algebra and simplify. Is
Yes.
that you have a canonical basis for the algebra.
Well,
so you
that's
can
exactly
write-
where we're going. Yes.
Otherwise, it's kind of useless with this formulas.
That was my point. My point was that this is useless, and even making a PBW type basis is still not so promising, maybe, but already much better. And so the only improvement I want to make about that is to write it as exponentials. But so to answer the other question, so in general, this is. right? So the Zn of a tangle takes values in the algebra tensor itself with as many tensor factors as the number of components. Yes?
Unless you get to the center or something, or degree 0, it's not an invariant.
It's a not invariant. Sorry, there was a problem. So I think your point is the same as Don's point, that I should use the relations in the algebra to bring this into some canonical form.
No, it's only a piece of that. Maybe the degree 0 piece after you use the relations.
Well, you're free to consider the degree 0 piece, but I want to consider all pieces right now.
No, but you seem to be claiming different things. He's saying the whole thing is not invariant, and you're saying it is. And it either is or it isn't.
Yes, and I'm of the opinion that it is an invariant, but I'm happy to discuss this later, and so I want to continue discussion. I want to move on to indeed bringing this in normal form, and so hopefully convincing you that this is a not invariant, but well, we will see. So I want to go to normally
Roland? So you know the center of the algebra, right?
I know it exists. I don't know quite what it is in this case. I have not considered it.
Because the all not invariants will be central.
Yeah.
Yes, if you have an argument, yes. Yes, so it would be nice to express the center, but I have no clear expression for this. Yeah, this is definitely something I'm looking for. So this normally ordered exponentials is just an elaboration of taking a PBW basis, right? So for idea number 1 is order variables. And to make ordering a bit more pleasant, I'm going to change my basis. So instead of the big B, use B equals, I already wrote it, this central element, so I want to pass to that, because then we have one less variable to order. So I'm going to change the basis, so we're getting rid of the big B. And actually, I'm going to also work over the ring Q. So I will write Qn, but in the handout it's Q epsilon. But so I want to take power series in this central element B. And so I'm going to change the algebra on you. This simplifies matters. It's not essential, but it's nice, and it is essential for getting something polynomial size. So that's the idea number 1, and I think this is pretty standard. For 2, this is to consider to write every as a perturbed ordered exponential. And so before I'm writing down the general statements, maybe we should consider example. This will be non-perturbed, but let's consider n equals 1. And let's see what the R matrix really looks like for n equals 1. Well, it looks exactly like this, except when n equals 1, then I get usual factorials. So that's a bit nicer. So it's this thing, but I insist to write this as, and so far this doesn't quite make sense, but I still insist to write it like so. This is not equal, right? This is not equal, and that's the whole point of ordered exponentials. So I want to make a theory of expressions for which. So this is not equal to that.
So you changed that to little people's genetic.
I apologize. I was trying to gloss over that. But indeed, I should have written. This is still the big U, not universal developing algebra, but here. So little b. So big B is little b plus epsilon c. Thank you for catching that. Ij. So now I did make the transformation. Big B to the I gets small b plus epsilon c to the I. Yes.
But if n equals 1,
N equals 1, yes, so epsilon
you can
equals
get rid
0.
of the little epsilon.
Oh, that's
You
true.
have little b.
That's true. Epsilon is 1 here, so you were
Oh.
right. Thank you.
Right,
That
good
I
point.
apologize.
Good point. And so my point about these ordered exponentials is that even though it's not of this form, it's not a pure exponential, I still want to use this imagery, and I want to make a notation so that things that are not true become true. Right, so this is a motivation for defining this object O of some power series that does model things like this, but it has this ordering, the alphabetic ordering built in.
But the right hand side is in dn, but dn tensor 2, right? What do you mean?
Yes. So this is definitely not equal. It's not even in the same space, as you said. But so the point of this thing I haven't defined yet, but I'm going to define, is that this will be an object where this is just a commutative power series in some variables, and maybe I can give the variables names 1, 1, 2, 2. Now it becomes a little bit clearer, and now the definition basically is to take this commutative power series and then order the things that have subscript 1, order them on the first tensor factor, and subscript 2 on the second tensor factor. And so it's just a way of writing complicated sums and sort of avoiding this mess from the very start. So I owe you an exact definition of this O thing. And this was one reason for making the handout, because it's kind of complicated. But let's go through it and see if it makes more sense than what's written here. I agree this doesn't make sense. This was for motivation.
But the argument, the O is a commutative thing now. Is that what you said?
Yes. And I will be.
Surely that's just true for any operator at all. I mean, this thing will not only depend.
No. So there is some. This is not an operator. This is my own device for what I call ordered exponential. So maybe the brackets should not be taken as O of something,
Okay.
but it's this is an ordering of the. So we have many terms here. It's a power series, and I'm going to take the power series and take all the variables and put them by hand on tensor factors.
It's similar to usual the normal ordering in.
Yes, I think so. Yeah. I mean that was the reason for naming it. So.
So we are using columns for both sides usually.
Okay. Yeah. Yeah, I think that's good. So we're sort of halfway the first page of the handout. So this is where the definition. So this is definition. O of f. And because things are linear, I will start with for f a monomial. Then if we know how to order monomials, then we can order sums of monomials and maybe power series. So I want to define f first. F is a monomial in some commuting variables. So f is product over some set, s in big S. So S is some fixed set that comes from the components of the tangle. S is a set. finite set. And here we get C, U, W, U, W, and maybe I should have done multi-indices, but I didn't. So this is all written in the handout with this big product. And here we get some exponents, Ks, Ls, and S. I see I forgot the coefficient. Of course, monomials are allowed to have coefficients, but again, this is a linear story. This is not going to affect anything about the ordering. So I do not have
So
coefficient.
linear over this new base ring. Linear over the
Yes, the new base ring. Although I could have, this is just because KLM is something nice, KLMN is not something nice, but I could definitely have, I could have avoided this B and just worked with the big B and done the same thing with 4 variables. It would have done the same thing. Yeah, it seemed nice to do it like this, but it's sort of arbitrary. Okay, so we have this thing, and now define. So it's O of f, but it's not operator O applied to monomial f, but this is something new and it's something non-commutative that lives in, it should live in dn to the tensor power s, so the cardinality of the set, and it is defined as a tensor product s and s, of some thing I called f sub s, not sure why. And f sub s is just, so maybe I can just write it right away. It's just c to the ks. So notice that the lower the subscript vanished, and that's the only thing that happened here. ms. You see, so it's exactly the same thing as the monomial, except the subscripts have vanished, and instead of the subscript, I'm taking a tensor product. So this is definitely in this tensor product of dn. And I suppose this happens a lot in this kind of algebra also when you write R1, 2 or so, that 1 and 2 also usually refer to the tensor slots. I just wanted to have a nice definition that hopefully correct. And so this generalizes for the 2 power series. In the same variables. So this is a way of making some commutative start and then making something non-commutative out of it. In the standard order, and of course we could have different orders and different O's, but I like alphabetically ordering things. Okay, so this generalizes, and so here's an example. And so this is in the spirit of this, but I can do slightly better. So this n equals 2. But if you want to see n equals 1, you just set epsilon to 0. So R, you can check, and you should check. This is O, this is also on the handout. But this is what I mean by a perturbed exponential, ordered exponential. So it's 1 plus, and then epsilon times, this is the perturbation, Ci, Cj. Oh, this is Rij. Cj Ui or Uj. And it looks a bit awkward, but this is because of the quantum factorial that has been changed into a usual factorial. This gives this last term. So this is the perturbation, and then we get the quadratic form BCJ. Oh, that's unfortunate. Let me write Q for quadratic form. Q equals BCJ. And this is actually linear because B is in my ground field, or in my ground ring. But the quadratic part is this. So this is exponential of Q. This is the end of the bracket. So this is the O of something commutative. And if I take the O of this commutative thing, I get something in, so this lives in in D2 and was 2, tensor D2.
But elements with the same labels do not commute, right? CI.
Exactly, yeah. Well, but inside here they do, but when I put them on the, then the labels are actually vanished. So, but yes, the answer is
So you put all C's to the left. That's the thing.
yeah, alphabetically ordering things. Yeah, it's a slightly awkward thing, but computationally I found it useful to work with this commutative object here and then keep the ordering apart. So in some sense this example is all you need to know and sort of all I have to say. Because you see, if you have the R matrix written like this, then it's conceivable at least that if you combine R matrices in the fashion we did for the figure 8 for the trefoil knot, that you will stay in this space of perturbed ordered exponentials. And so that's the point of theorem 1 at the very bottom of the handout. Is that indeed for n equals 2, for any tangle it will have roughly this form. So you can write this invariant Zn in a standard canonical form.
But it's very. The commutative algebra is much smaller than the non-commutative algebra. No.
I agree.
No, it's not. No.
Well,
No, it's not because all the commutators are inductors. So, in a sense, it's the same size.
I'm not sure what you mean by signs.
Well, if you take the graded dimensions, for instance, are they equal? But I guess they are equal because all your commutators in some order are
Yes.
smaller or not smaller.
Well, I haven't considered this question, so I
mean,
should think about
it. Doesn't really make sense because unless O is an isomorphism,
But so
you can't write everything as O.
No, you cannot. But so we start from something that you can, and then the content of theorem 1 is that you stay in this very nice little garden, so you don't go outside. So there are definitely objects in D2, tensor D2, that cannot be written as this perturbed thing, but we just get lucky, I think. There may be a deeper reason for why we stay in this space.
But if O is injected, then you can just drop the O and you'll find an invariant that the commutative algebra is a much easier thing to work with. Yeah.
Maybe so, yeah.
You can just drop the O completely and say the invariant you're interested in is the thing that your original thing was the O of. And then you just.
I think that's a good point. Yeah. Drop the O. It will. Well, I would get more confused, but indeed it will. At some point, it will be less confusing. I hope. So I made some statement here about. So this is theorem 1. Is that for any T, for any tangle T, we have it's O of 1 plus epsilon P. This is the perturbation. This is the Alexander polynomial of the tangle delta, or it's just the Laurent polynomial maybe for now. Times e to the q, where P is the quartic in and they're also balanced in some sense, but the general feature is that they're quartic. So quartic in the sense that I forgot a square here. So here you get ui squared wj squared. So that's what I mean by quartic here. And delta is in q. Well, morally it should be in power series in b, but it's actually a Laurent polynomial in t, where t equals e to b. So we get another bonus that we get to work with Laurent polynomials, and so this is the Alexander polynomial. It turns out I had planned to do the trefoil knot example explicitly on the board, but I think I would need at least 15 minutes for that. I don't have that, so I'm happy to show it to you later. But I will now just invite you to turn the page and look at the ugly side of things, because you may wonder, okay, this is great. Why not do 3 or do 4 or do n or do everything? But maybe do UQSL2. Maybe it's true for UQSL2. But there's something nasty here, at least nasty or beautiful. I don't know. But this is at the top, at the bottom of the page. It's called. I call it logos. And it's this 5-line, 1, 2, 3, 4, 5-line polynomial in many variables. And logos means it's the order of the universe. And so this is what makes it work. This is the scaling relation, in some sense. And this is at the same time. I'm claiming this is simpler than the scaling relation, but it's also much worse. And I think it can be simplified, but I haven't understood it right. But what it is this is a way of, this is all you need to commute these ordered exponentials past each other. Because suppose you have two R matrices. These are very nicely ordered, so this is the O of something, and this is also the O of something else. But now what if I do this? Then we are supposed to read from the definition of the universal invariant. We're supposed to read whatever we see along the line. And so here we have a nice order CUW, but here we also have a CUW order. And so now we got a clash between orders, and I actually wrote it incorrectly. But so the purpose of this logos is just to change the order in. So there's this joke, you have 2 cows and you make 1 cow. So in Dutch this is actually koe, which is phonetically quite correct. So you have this is inverse Banach-Tarski, you have 2 cows, you make 1. And for that you need something very fancy, you need the principle of the universe. And that's this 5-line polynomial. But so let's not stare at it too, but let's go briefly to this lemma 1. And this lemma 1 is a complete implementation of this problem where you want to stitch R matrices together or tangles together to build a knot. And so what you have to do is you have to deal with these things, but not just the ordinary letters in the Hopf algebra, but at the level of exponentials. So we want to do things like e to the u. And this is actually not so hard. This is this. Is it called Heisenberg? Here we just get the commutator of u and w.
It's the same.
Oh.
No, it's true.
Yeah.
Yeah.
But what are the indices? 1, 2, up there?
Well, for this discussion, I don't really need indices.
No, in the upper line.
That is just number.
Well, so the indices came from that I have some component 1 here and a component 2 here, and then at first they are not connected.
Okay, but when you connect them,
They are in the same algebra, so I should really
I see.
just erase them. But the indices are useful for keeping track of the order. And so, but then we have to deal with them in one algebra, and then we have to reorder. And that's the name of the game. And well, this game is surprisingly well. At the same, for the computer it's very easy. For humans it's maybe harder. But so this lemma 1 does everything for you. And maybe rather than reading all the formulas, I can just point you to, this is a generalization of this O thing, and you should pay attention to, in the lemma it says things like, here you have something, and then here it says CUW, CUW. And there are 2 bold letters, and the bold letters are the process of changing this into CW. So I changed these 2. Now I should change U and C maybe. And then finally I should change W and U to get C, C, U, 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 W, W. Right, and then we can merge the C's and the U's to get C, U. So there are 3 steps necessary, and these are the 3 points in the lemma. The middle step involves this logos, polynomial, and this is the reason why it's not so easy to generalize this to 3. It's definitely possible, but it would involve a better understanding of this logos. And I think that's an interesting object here. And it looks complicated, but at the very end you see there is actually a program here. And so I'll just end by saying that this is expected runtime number of crossings. So that's polynomial time, but it's still at 7. So that's not as good as the Alexander polynomial, but this is a stronger invariant that could be computed for many knots. So we'll give maybe some interesting supplements to the many experiments we have been doing in Fourier conjectures and other conjectures about the Color-Jones polynomial. So I think this is a good time to stop, but I should note that this is only the beginning. Right? There are many things. Maybe I can write down the invariant of the trefoil. That's maybe a nice ending. So this is Z2 3-1. There you see some of its features. So delta is the trefoil Alexander polynomial, right? So this is T. Maybe what a plus here, and maybe over T. So there's still some choices here in normalization. So this is a plus. There are 3 terms, and it's a minus actually. -2. I don't know why I wrote T minus 1, but no. Easier. We're done. So I computed for the whole Rolfson table, but
So the Q of your theorem is just 0.
so T.
The Q of your theorem is just 0. No, T is.
Q of my theorem.
You have a theorem in the handout. The theorem says that there's an exponential term e to the Q.
You're
And
absolutely
here there's no
right. So what I'm
exponential.
writing down here is only the P. So this is P.
Oh, this is P.
Yeah. So this is the P part of. Yeah. Excuse me. The point is that the Q term is the same as the Q term for Z1, so that's why it's not so interesting. But so this is the P part of Z2. Yeah, thank you very much. Otherwise, this doesn't make any sense. But so this is the perturbation, and so this is the new stuff that comes out.
So when you say quadratic, you mean at most not a quadratic form, but just degree smaller.
Quadratic. I mean quadratic for Q, right?
Quadratic. No, you call P quadratic and Q.
No,
quartic.
quartic.
Yes, but you use the word quadratic and quartic. You don't mean quadratic forms. Therefore.
No, I just mean degree 4 at most 4.
Most forms. It's not homogeneous.
Yeah. But it's kind of surprising that it has only a C and a UW. So there could be a U square for all we know, but that could be. I mean, this P is better than quartic, right? This is only a quadratic P. Well, it's degree 2 in UCW. So there are some surprising things. There are also some Alexander polynomials pretty much all over the place. But there are also slightly new things. And yeah, I think this is a good time to end. Thank you very much.
Sorry, did you say that large Q is independent of n from n?
Yes.
Oh, I see.
So it's really the Gaussian term, and then the perturbations will get stronger and stronger depending on how big n is. And yes, and the same is true for this constant term. This constant term will also be always 1 over Alexander. I expect that, at least for n equals 2. So this, I really mean 1 over Alexander.
But you don't know that the theorem is true for bigger n.
Right, I know very little about bigger n.
No, I'm just asking if the theorem is true, not how to compute it.
Um,
In other words, is there a universal P1, P2, and you get 1 plus epsilon P1 plus epsilon squared P2? Or do you just only know the first?
I think so, but I have no theorem. No. But there are reasons to think. If you think about the Konchevich integral, then there is some reason to think about this. But no, I should say no. I know very little past n equals 2 so far. Yes.
So the two-loop invariant is a rational function or polynomial in T.
Yeah, it should be
But
in
it's
here.
one polynomial in T.
Yes,
And
and-
there I see 3.
But it could very well be that this one and this one are sort of following from this one. I'm hope. Or maybe there's another way of twisting it or presenting it. But you're right that there seem to be 3 polynomials where we only were hoping for 1.
For 1, yes.
So there should be dependence, and this was one reason for computing many examples to see if there was some dependence. But so far, well, there's some clear patterns. There's always this t plus 1 or t minus 1 coming up, but it's too early to say. But I agree with you that it should
There
not.
should be only 1.
Yeah.
Isn't it better to have more invariants?
Yeah, but then if I know this may follow from some argument. Yes.
Where do you need epsilon to the n equal 0? Where do you need that epsilon to the n equal to 0?
Improving lemma 1. So lemma 1, and mostly in the second part of lemma 1. But in some sense you don't need it, but it just simplifies matters a lot. Because if you think about commuting these exponentials past each other, these are ordered exponentials. So what this really means is well, I was going to write them as power series, but I think that's pointless. The reason I need some nilpotency is that I can really sum the geometric series still, and then and some derivatives of this geometric series. I think that's one way of saying it. So if you didn't have that, then you wouldn't get it. So for example, if I write the Q exponential, I don't know, an, then usually this is not so. Well, it is just what it is. But now we can write it as the usual exponential, and then some perturbation, and then we can use the usual exponentials, which I.
Yeah, but that is true. You have epsilon series in it.
Yeah, so maybe I'm just slow. I'm hopeful, but well, again, this logos thing came from commuting these exponentials. That seems to get out of hand a bit. But maybe again, this is because I'm using the wrong basis or the wrong viewpoint. It's definitely possible and tantalizing to see if it goes all the way. Yes.
I thought Drower's method, at the end of the day, for one knot, produces a rational function in one variable.
So the rational became Laurent.
Yeah, Roland. Yeah, it doesn't matter. But the denominator is known, so you can get a polynomial, but you still get 3.
Well, so we both wrote a program from slightly different algebras, slightly different perspectives, and so actually for the trefoil and for Allmans we computed it, they do coincide. So there must be some uniqueness of the R matrix. So the invariant, so Dror also gets 3.
It's 1.
Well, so I wrote a link to his website where you can see his program, so you can run it for yourself. That's very interesting, I think, and it's definitely not the final product. There should be something here, and maybe it's related to this remark about the center. It's at least unclear to me what is the center of this algebra. That would probably help. Yes.
Yesterday when Stavros mentioned a program that worked for things with up to 24 tetrahedra, you complained that that's not really computable because after all there must be 100.
Yes, I was trying to promote my own talk.
Now you
It
seem,
was very
and then you
selfish.
said tomorrow I'll show you something that really is computable. Now you seem to say you can only do the trefoil. So you can do billions. Yes, but
That's quite good, right?
well, I don't know, but he can do billions and you can only do one. So
Well, I did one. I wrote one on the board, but I have a computer program, so that can do billions too.
it can, it has.
Well, I did not do
Everything can
billions.
if you let it run for billions of years. The question is whether it actually works.
It actually works, and so far I computed for the Wolfson table, just because that was in my reach. But any braid presentation, so you're welcome to give me your favorite braid, and then we can hit enter.
So what if you could just take a knot with 10 crossings, then you actually get an answer?
Yes.
For a finite amount of time?
Yes, 20 seconds or so. My computer is old. But yes, and I'm happy to demonstrate if you want to show it. I can show
You
you.
just said triumphantly that you and Roland both computed for the trefoil and you got the same thing, as if that was sort of the limit.
Well, this was the first thing, so that was
Can he
exciting.
also say something with his program with 10 crossings and get the same thing?
I think so, but he didn't implement the inputting a knot automatically. So and I did. So, but yes, I think there's this theorem that if you have an R matrix, then no matter how you twist it, it's going to give only one invariant.
So really this bound number of crossings to the 7 is fictional.
Maybe.
I mean, in practice, it's not 10 to the 7.
So if you have Alexander, then you would do. So Alexander would be number of crossings to the 4, right? So this is worse than Alexander, but still pretty good, I think. So I don't know. I'm not a. So to me, I'm honestly I don't care so much about computation, but I think this is a philosophical point that it is not an exponential runtime. So this must be a simpler object than the objects like the Collar-Jones polynomial. And so it may be worth studying what exactly the runtime is. But it just shows that it is a different way of thinking about knots.
So it's polynomial for any n, right? For any n.
Yeah. And so I'm happy to demonstrate, and you can give me a braid, and I will compute it.
And how the exponent grows with n?
Wait. So the number of crossings to the 7.
No, for gn.
So sorry. So far, I was only able to do n equals 2.
But for any n, it is a polynomial, right?
I expect so, but I have not. Because again, it was sort of painful to derive these logos correctly. So I derived it 10 times or so, and 10 times it was wrong, and I checked it with the computer and sort of merged all the mistakes and got something that actually ran. Experimental mathematics. But there should be a better proof, it's just that I'm not very good at it.
No more questions? So, thank you to the speaker. The next talk will start 11:30.